Hello everyone. So in today's class we will try to understand the basics of electrostatic field, and we will also try to understand the flux and the Gauss's law. So here we can see a picture where two charges are being shown, and we see some lines getting emanating out from the positive charge and going into the negative charge. So in the previous class, we have talked about the continuous charge distribution. Like if we have a line charge distribution, we have a surface charge and a volume charge distribution, then how exactly to calculate the electric field, and we have come to know that these are the equations which will help us to get the electric field. Now in a sense, we are almost done. I mean, if we have to talk about the electrostatics, then this much is sufficient for us because we have already evaluated the electric field, which is the prime question of concern. Thus, in a sense, we are done in an electrostatic. However, the point of concern is that even for a simple charge distribution, these integrals involved may be formidable. So, why they are formidable? Because the integrals are not very easy to calculate. For example, if I give you a charge distribution of a complex nature, so for example, rho r, which is a very complex function of r, in that case, it would be very difficult to integrate upon the rho r in the volume charge density, or not only in the kind of a volume charge density, even if you have got a surface charge density, then also it will be very difficult for us to evaluate the calculate or evaluate the integral. Hence, the rest of the electrostatics is just to create some tricks and tools which can be employed to get rid of such complexities. Means, in what way we can circumvent the problem of calculating the integrals. That is what is our concern in rest of the electrostatics. So whatever we will deal up in the next class and so forth, we will just try to figure out certain kind of a rule or certain kinds of a tool we will like to develop so that we can cross or somehow in a get away with the complexities involved in evaluating the integrals. Now let us try to feel the electrostatic field. So far as now we have tried to understand what is an electrostatic field as of a point charge, which is given by the expression q upon 4 pi epsilon naught r square. But how exactly the field falls off at large distances? So we know the field falls off at large distances as 1 upon r square. Clear? Now to get a field, we draw a few representative lines. Now let's consider here at the center you keep a charge which is essentially positive because electric fields are going away from it. So if this is a positive charge, then electric field has to fall off as 1 upon r square. Suppose this is r, this is electric field, so it will fall off like this. So what we have done, we have represented the electric field with some vectors. Now near to the center or near to the origin, we have drawn long lines. That means the electric field is of high strength, and as we have gone away, the lines are getting shorter. That means the magnitude of the vector is getting lesser and lesser, which itself means that electric field is having less strength or less magnitude here than at this point. Now how many lines you can draw? As many as you wish, because it depends upon your skill of drawing and the sharpness of pencil, how many lines you can actually draw. But one thing is sure, that the field line is seen to fall as 1 upon r square. So now why we have shortened the vectors? Because vector, as we know from the very basic concept of vector, that vector's length actually gives a sense of magnitude of the vector. Now if I draw two vectors, now vector A is having more strength as compared to vector B. So wherever we had to measure the electric field to be, or we have to mean that the electric field is falling short of its strength, then we have decreased the length of the vector. Now, there is another way of doing it. So let us now try to connect the lines together. For example, you have got a positive charge here, you have got a negative charge here. There is another kind of a representation which you can make, where you can see the lines to come out from the positive charge and get entered into the negative charge. But while doing so, there may be a concern that perhaps we have neglected the information on the strength of the electric field. Because in the previous picture that I have shown, there the vector diagram was made for the electric field to represent a charge, and in that case, as we have gone away from the charge, we have decreased the length of the vector or size of the vector, which itself means that the field has decreased as 1 upon r square or so at large distances. But in this case, there is no such thing. Lines are continuous lines and they have started from one charge and gone into the another charge. So you might feel that I have neglected the information on the strength of the electric field vector, but actually this is not the case. Why it is not the case? Because the information is hidden somewhere else, where the information is contained in the density of the field lines. Now, what is the meaning of density of field lines? So, for example, look at the field lines right at this particular position. If I draw a circle, in that case, you can see here for this particular circle, there are almost 1, 2, 3, 4, 5, and 6 kinds of lines which are going through this particular circle. Now, if I make a circle similarly over here of same size, how many field lines are actually going? 1 roughly, or at best 2. So that is the reason why the density or number of lines crossing per unit area in this case is less. So strength of the electric field, that information is contained wherever the density of these lines are stronger. So their electric field will be stronger. Wherever the density of lines are falling away, there the electric field strength will also fall away. So you can see at large distances, this density of lines are actually falling. Clear? Now there is, however, a small deceptivity or deceptiveness. What is the deceptiveness? That field lines in two-dimensional structure is actually deceptive, because if we draw field lines emanating from a circular configuration, then the density of lines passing through the circle is simply the number of field lines divided by the circumference of the circle. That means how many lines are actually passing per through the circumference of the circle. For example, let's consider a geometry like this. Although it's not a very good circle, but consider this to be a good circle, and there is a positive charge, there is somewhere a negative charge. So for example, here, in that case, what will happen? The charges, the lines will come out and will go into the negative charge. So it will come out like this. Now if I ask what is the density of lines, density of lines is given by number of lines crossing this circumference. So in that case, what we will get? We will get n depending upon n upon twice by r. So it falls off as 1 upon r. But what is the electric field falling on? Electric field falls off as 1 upon r square. But here we are getting that strength of electric field is falling as 1 upon r. So that is the reason why this particular picture or diagram, although we represented it in two dimension because we are bound to do that, but the conception itself in two dimension is little deceptive, because actually the charges, whenever you keep, suppose in a corner of your room you have kept a charge, then it's a three-dimensional problem. Although we represent it in two dimension, but this is a three-dimensional problem. So whenever we do it in three-dimensional, we do not fall into that trick. Why? Because in three-dimensional you do not have a circle, you have got a sphere, and the sphere area is 4 pi r square, and you can see the strength is falling off as 1 upon r square, which matches with the fall of electric field at large distances. All right. Now you might think, okay, in 2D representation also we could have taken the area. Why you have considered the circumference? The reason is, once you consider the area of a circle, then this whole lines are actually, or the whole region is to be considered, which is actually equal to pi r square. But in this case, if I keep a charge somewhere here, then whole region doesn't come into action, because we are only concerned with how many lines are actually crossing this kind of boundary. So since we are only concerned about the boundary line of the enclosed surface in two dimension, in that case suppose, then it is the circumference which comes into action in two dimension. But in three dimension, it's an enclosed surface. That means we get a volume entirely, like a football. So we get the surface area as a whole. Why? Because the lines, if you keep something within the center of a football, then electric field lines will come out through the entire surface of the ball. So that is why you have to consider the area, and hence you get the strength to fall off as 1 upon r square. So actually remember this in mind, that this representation of field lines is totally workable in three-dimensional conception, or it rather works in three-dimensional conception, although we make a two-dimensional representation, but it should not be thought as a 2D problem. It should be always considered as three-dimensional problem. I hope this part is clear. Now this is a figure where we have compared two different charges. If it is a positive and a negative charge, then we can see field lines are coming out from the positive and getting inside the negative charge. But if there are two positive charges which are kept face to face with each other, in that case electric field will come out of the positive charge in both these scenarios, and in this case we can see the field lines are not crossing each other. So I hope in plus 2 level already we have come across the properties of the field line, and this rather I would like to give you as a homework. So homework is, do it for yourself, get the properties of electric field lines. All right, in this case there is a very famous question that why do electric field lines do not cross each other. For example, here you can see they have got away with each other, away from each other, but they have not crossed like this. Why this crossing is not possible? This is also a question, because if it crosses, in that case in this particular point electric field will have two different directions, one is this, another is that, and this is not possible. At a single point electric field is a point function, that means it will have only one single value. So that means at a single point it cannot give you two different directions of the electric field. This is not possible. This is self-contradictory. So that is the reason why they will, if you keep two positive charges face to face with each other, the electric field lines would rather like to go away from each other rather than crossing each other. All right. So that's all about the feeling of electric field lines. Now let us come to the understanding of another quantity called electric flux. Now flux means what? Suppose in any kind of a flux not necessarily, do not feel it that I am only talking about electric flux. Flux could be of anything. It can be a charge flux, it can be a particle flux, it can be electric field lines, the flux of lines. So whenever I call this term flux, it is always meant that it is the flow of something per unit area per unit time. So there are two different entities which are involved. One is the per unit area, another is per unit time. There should be a comma over here. So if you talk about the flux of electric field, in that case it is the number of field lines crossing per unit area per unit time. If I have to talk about a particle flux, then it is number of particles crossing per unit area per unit time. It is something like that. So electric flux is a measure of the number of field lines passing per unit area per unit time. And how do we represent that? We represent it as a surface integral. This integral means surface integral E dot dA. Now what is a dA? dA is a small elementary area. Now let's consider this is a small elementary area. These are the electric field lines which are going through the this particular surface, and let's consider that they make an angle theta. So this dot product, there is a significance of this dot product. The dot product picks out the direction of the electric field which is along the area vector. That means, what is the meaning of a dot product? On the other class we already talked. The dot product means how much two vectors are parallel to each other, and if you take the dot product, then it selects the component of one particular vector in the direction of the another vector. All right. So if electric field is completely parallel to dA, that means theta is equal to 0, then dot product will become maximum. That means E dot dA, which will be equal to E dA cos of theta, theta cos theta equal to cos 0. In that case cos 0 is equal to 1, so you will remain with E dot dA to be equal to E dA. So that is the maximum value of the dot product. If the field lines are perpendicular, so for example E is going in this direction, dA is in this direction, in that case it will be pi by 2, 90 degree, and cos 90 degree is 0. So that means flux will be equal to 0 through this surface. So dot product actually picks up the direction of the electric field which is along the area vector. All right. Now that means we get the maximum flux through an elementary area if the angle between E and the elementary area is 0. All right. Now you have to integrate it. Why? Because dA is the elementary. Suppose this is the complete area through which you are uh, about to find the electric flux, and you have considered only a small area vectors. These are all dAs. All right. These are all dAs. Now what is the total electric flux through this complete area? That will be the integral of all these electric fluxes which go out of these small dAs. So you have to integrate upon this flux which is E dot dA over the entire surface. Then only you get the total flux phi E. Alright. So E suffix over here I have written because it means actually the electric flux. So thus flux through a closed surface is a measure of how many charges are there inside the volume of the closed surface. Why? It's because where from these electric field lines otherwise will come. So in that case it has to come if there are charges. For example, if it is a closed surface and you are getting some field lines out of this closed surface itself, then it itself means that there is some kind of plus. Now there could be one plus charge, there could be two plus charges, three plus or four plus charges. That depends upon the situation. All right, but there is definitely some kind of plus charges which are there within the closed volume. If you see that electric field lines are coming within the volume, then you rest assured there are negative charges within the volume. So if you get some flux out of a closed surface, then that means that there is some kind of charges which are there within the volume, or the volume contains some kind of a charges. It could be a single charge or a charge distribution, that depends on the situation. We may not talk about it right away. Now this gives us the foundation of something which is called Gauss's law. Now what is a Gauss's law? The statement goes like this: electric flux through any closed surface enclosing a charge q is q upon epsilon naught. Very simple and elegant. So what it says, similarly as already I have said, suppose you have got a spherical ball where inside you have kept a charge plus q, and you see that certain electric field lines are coming all throughout the surface. I have shown only few lines, but it's coming all throughout the surface. In that case, the flux, overall flux, is given by phi e, which is equal to q upon epsilon naught. That means number of charges which are enclosed by the surface, closed surface better, upon the permittivity of free space. Now how can we prove that actually? Because we have learned that phi e is equal to integration EdA. So how come this integration is going to give you q upon epsilon naught? Let us try to see it. So let us consider a spherical geometry. For spherical geometry, dA, the area element, is given by r square sine theta d theta and d phi. All right. So what is theta and phi? Theta and phi are nothing but r theta phi coordinate we are solving. So suppose there are this particular thing is phi. Suppose this is a sphere, then this angle is theta and the radius vector is r. So r theta phi coordinate, you can just search it in internet, what is an r theta phi coordinate for spherical geometry. Similarly in cylindrical geometry you have to work with r theta and z coordinate. Since here we are working with spherical geometry, we will work with r theta phi coordinate. You just remember that area element in r theta phi coordinate or spherical coordinate is given by r square sine theta d phi. So what is the electric field? That is, we know q upon 4 pi epsilon r square. But the electric field and the dA both are the vectors which are radially outward. That means along the radius. So that is why I have kept here r cap. So r cap dot r cap will give you 1, and you remain with 4 pi epsilon naught r square sine theta d phi. If you resolve this integral, if you solve this integral, then you will definitely get it to be q upon epsilon naught. All right. This is, by the way, a double integral. Once you have to integrate upon theta, then again you have to integrate upon phi. So for integration upon phi, the limit has to be taken to be 0 to twice pi, and in this case 0 to pi. All right. So that's what is actually the total evaluation of this integral, which will give you q upon epsilon. You can try it for yourself. If you in case face difficulty, then definitely I will come to your help. Now this is an integral form of the equation. For example, let me just rub everything else in this particular slide. So how do we write the Gauss's law's integral form? Gauss's law in integral form is given by closed integral. Remember, this is a closed surface integral, so I should also write an s over here. E dot dA is equal to q upon epsilon naught. This is the integral form of the Gauss law. Remember this term. Then how to get the differential form? Differential form is obtained as, suppose you do not have a charge, rather you have a charge distribution, means lot of charges are getting distributed over here, so that you get a term called rho of r, which is a volume charge density means charge per unit volume, then charge can be obtained from this particular expression as integration of rho d tau, where tau is the volume. So Q is equal to rho d tau, and by using Gauss divergence theorem you can convert this surface integral into volume integral. So if you put it in that case, this is the volume integral which you got out of conversion by using Gauss divergence theorem, and on the right hand side 1 upon epsilon naught remains as it is, and you remain right here as integral rho d tau. So since both the sides are having volume integral, their integrands, that means the quantity which is inside, this dot should not be there, by the way, this dot also should not be there. The integrands which are there inside, they should be equal. So you just write del dot equal to rho upon epsilon naught. So this is the differential form of Gauss law, and that is the integral form of the Gauss law. All right. So today we will stop here. Please go through these slides and go through this video carefully, and next time we will come up with some other topics on electrostatics. All right. Thank you so much.